Hello. In this video, we will cover section 8.2, which is on hypothesis testing. In the previous section, we outlined the hypothesis testing process. In this section, we will go over the process in more detail so that you can actually implement it. The first step is the hypothesize step. We turn the statistical statement into a pair of hypotheses about a population parameter. We've gone over that. In the second step, we are going to go through and collect or examine data. And one step that we're going to introduce in this section is that we're going to check that the data meets the central limit theorem. In the third step, we're going to go through and we're going to analyze the data by stating a significance level and calculating the test statistic, which we've done. And then we're going to go through and find the p-value. That's going to be new. And then in the fourth step, we're going to go through and we're going to use the p-value and the significance level to determine whether to reject or not to reject the null hypothesis. Okay, so let's go through each of the steps one by one. So, well, for the most part, each of the steps, because immediately we're going to say step one, we covered step one in sufficient detail in the last section. So we're actually going to skip over step one, but we're going to go through steps 2, 3, and 4 in some more detail. All right, so we ended the previous section with the need to go through and calculate the p-value. That's the last thing that we did. And so what is the p-value? That's the probability of an outcome as or more extreme than the test statistic. Since the test statistic is a z-score, we want to be able to turn a z-score into a probability. That's what we're trying to do. So we've got a z-score, we want a probability. That should sound familiar because we've done something like that before. We turned z-scores into probabilities back when we did normal distributions. However, if we're going to do that, we need to have a normal distribution. We can't just do that with any old distribution. Fortunately, we discovered in the last chapter that a sampling distribution, that is something that's a sample from a population, will be normally distributed as long as it meets certain conditions. That is what we call the central limit theorem. That means that if the data that we use in the hypothesis test meets the central limit theorem conditions, we can go through and use a normal distribution tools. We can go through and use normal distribution tools to translate the test statistic into the probability, into a p-value. Okay, so that's what we're going to do in step 3. So we're still dealing with step 2 here. So, but what we're going to do is, so in step 2, we're going to introduce this step where we go through and we check the central limit theorem conditions, so that in step 3, we can use the normal distribution to turn the test statistic into a probability, the p-value. Okay, so what are the central limit theorem requirements? So let's just review them. So the sample needs to be collected randomly. You have to have a large sample size. It needs to be large enough that we have 10 expected successes and 10 expected failures. And you can see that's just a formula there. You can go through and plug in the information from the hypothesis test and just make sure that it satisfies those two inequalities. You have to have a large population. The population needs to at least be 10 times the size of the sample. And then the observations have to be independent from each other. They have to have, so one success can't affect another success, another observation. Okay, so let's go through and do an example. So in the last section, we looked at an example regarding the percentage of Americans that own homes. We were told that in 2005, the percentage was 69%. Economists wanted to test whether the market had recovered to this level. A random sample was collected of 2,000 households that showed that 63.5% owned their own home. We came up with rival hypotheses that p equals 0.69 is the null hypothesis, and then p is less than 0.69 is the alternative. And so what we're asked to do, the new thing that we're asked to do, because all that was from the last section, we're asked to go through and check the central limit theorem conditions to determine whether the test statistic would follow a normal distribution. All right, so what are the central limit theorem conditions? So random, is it random? We can go through and say, oh, yep, it is random right there in the description. Is the sample large enough? So if we take the population amount, which is 0.69, multiplied by the sample size, which is 2,000, we need that to be bigger than 10. Then take 1 minus the population proportion, then multiply that by the sample size, and that also needs to be bigger than 10. Oops. There's a little mistake there. This should say equals 620 and then greater than or equal to 10. And then finally, the large population. So the population needs to be at least 10 times the size of the sample. So our sample is 2,000 households, and certainly there are much more than 20,000 households across the entire, this is Americans across all of the United States. And then finally, there's no way for us to verify the independence of the individual observations and the independence of the households from each other in the sample. So what we're going to assume the pollster did meet this requirement, but you'd have to talk to them in real life. Okay, so now we're good. So that's it for step 2. So we've gone over the new thing that we're doing in step 2, and that's checking the central limit theorem conditions. So now let's move on to step 3. So the first part of step 3 we covered in sufficient detail in the previous section. That is calculating the test statistic. So we're not going to do that again, just restating how you do that here. All right, so the new thing that we're going to do is we're going to go through and translate the test statistic into a probability. So this is the probability of getting an outcome at or more extreme than the test statistic, assuming the null hypothesis is true. All right, this is called the p-value. To translate the test statistic into the p-value, we use the normal distribution calculator in StatCrunch. There are 2 main cases that we need to look at depending upon the type of inequality that is used in the alternative hypothesis. So one is called a one-tailed test. This is where we have just less than or just greater than in our alternative hypothesis. All right, and that's what that says right there. A one-tailed test finds the probability that is in the tail that matches with the inequality. For example, if the alternative hypothesis is p is less than p naught, then the one-tailed test is going to find the probability that is in the left tail. All right, so recall that the probability for a normal distribution is the area under the curve. So what we want is we want to go through and find the area under the curve that's in the appropriate tail. If we were looking at this example, it would be in the left tail that is at or more extreme than the test statistic. To do that, what we're going to do is we're going to load the StatCrunch normal distribution calculator. We're going to leave the mean and the standard deviation alone. We're going to select the inequality that matches with the alternative hypothesis. That makes it easy, right? So if the alternative hypothesis is less than, then use less than in the normal calculator. If the alternative hypothesis is greater than, then put greater than. Then you're going to enter the test statistic value next to in the blank space next to the inequality, and then press compute. Okay, so that's for a one-tailed test. Now let's talk about a two-tailed test. If the alternative hypothesis has a not equal to, then it's called a two-tailed test. A two-tailed test finds the probability that is in both tails that is at or more extreme than the test statistic. I can't say that for some reason. To do that, load the StatCrunch normal distribution calculator, then select the between option at the top of the calculator, leave the mean and standard deviation alone, then enter the negative version of the test statistic next to the left inequality and the positive version of the test statistic next to the right inequality, and press compute. The probability that is displayed is the amount that is between the tails. It's not the amount that's in the tails. So to go through and find the probability that's in the tails, you need to subtract the displayed amount from 1. Okay, so let's go through an example of finding a p-value. So now we're going to go through and we're going to recall the claim that spinning a coin leads to a biased outcome. So that's a claim that we had in an earlier video. Our hypotheses were p equals 0.5 and p is not equal to 0.5. So we're saying that this coin is biased. So it's not equal to 0.5. We spin the coin 20 times and get a sample proportion of p hat equals 0.35, which led to a test statistic of z equals negative 1.34. It tells us to go through, assume the central limit theorem conditions are satisfied, and then it wants us to go through and find the p-value. So this is just giving us a bunch of stuff, and it says go through, calculate the p-value. How do we do that? So you load up the StatCrunch normal calculator, you select between. So that the reason you select between is because we have not equal to. This is a two-tailed test. Enter the test statistic, both on the left and on the right, the negative version on the left and the positive version on the right. And next to each inequality, and then go through and hit compute. And don't change the mean or the standard deviation. When you do that, you're going to get 0.8197, all that. So this is the area slash probability that is between the tails. It's the middle part. So we want the area slash probability that is actually in the tails. So we want to go through and take that. We want to go through and subtract that result from 1. And if we do that, we get about 0.18. So that's saying that the p-value is about 0.18 or 18%. How do you interpret this? What is this? What is the p-value? The p-value is the probability that we get an outcome of 35%, the probability that we get the sample outcome. So the sample outcome was 35%. So it's the probability that we get the sample outcome, assuming that the null hypothesis is true, which is that the percentage of heads you should get is 50%. So what is the p-value? You start off, you assume the null hypothesis is true. You assume that when you spin a coin, you get 50% heads, and then the p-value is the probability under that assumption that you get the sample result, right? The 35% that we from when we actually went through and spun the coin 20 times. So that is what the p-value is. It's the probability that you get the outcome from the sample, assuming that the null hypothesis is true. And there's a picture. All right, so there's a picture. This is what you enter into StatCrunch. So you got the negative 1.34 and the positive 1.34, and you can see the 0.8197, and you can see the shaded stuff that it's between the tails where we want what is in the tails. Okay, and so now next we're going to go over the step 4 in a little bit more detail. So for the final step, we choose between the rival hypotheses. And we're going to go through and we're going to use the significance level as the measuring stick in that choice. So option 1, if we assume the null hypothesis is true and then get a very small probability, smaller than the significance level, then we reject the null hypothesis. We say the null hypothesis was wrong, and then that suggests the alternative hypothesis was correct. Option 2, if we assume the null hypothesis is true, and then we get a large probability, we go through and we do an experiment, and we get a large probability, so that's what you'd expect to happen, a number that's larger than the significance level, then you fail to reject the null hypothesis, and that suggests that the null hypothesis is correct. All right, so to use the previous result as an example, if the significance level is 5%, and then you get an 18% p-value, 18% is significantly larger than the significant. 18% is just larger than the significance level. Let's not get into significantly larger. 18% is larger than the significance level. So then you'd go through and you'd fail to reject. You've got option 2 here. The percentage you got is larger than the significance level. So you fail to reject. That suggests that the null hypothesis was correct. All right. So what was that? Was that that's the last one? Yeah. So that suggests that with an 18% outcome, that suggests it's possible that it was just random luck that you got 35% of the coin spins as heads rather than bias. So that's the way to interpret that, is that if you get a high percentage, that suggests that the null hypothesis was correct, and it was just luck that you got the outcome that you did, and it does not suggest that the alternative hypothesis is correct. Okay. So next, the last thing we're going to do in this video, we're going to go through the whole entire process, the entire thing from beginning to end. We're going to do 3 examples, so that you can see the whole thing all in a row. All right, so in one Florida election, 47% of all registered voters voted. Researchers studying the behavior of academics asked this question: do political scientists turn out to vote in the same proportion as the general population? That's a very good question. To answer this question, the researcher took a random sample of 54 political scientists who live in Florida. It turns out that 40 of the political scientists voted, which is a sample proportion of 74%. And they want us to go through and conduct a hypothesis test with a 5% significance level to determine whether the proportion of political scientists who vote is higher than the general population. Step 1, we need to create our rival hypotheses. All right, so we need to go through and read the problem, identify what is the population percentage, and then we're going to use that and in the null hypothesis, and then we need to figure out the alternative hypothesis. So give it another read here. So 47% of all registered voters, if you go through and skim through that, That is our population. And what are we trying to figure out? We're trying to figure out whether political scientists vote in a higher percentage. That's our guess, is that they vote in a higher percentage. And so that is what we put in the alternative hypothesis. All right, so you've got P equals that 47%. And then our guess, what we're not our guess, but we're checking is that the proportion of political scientists who vote is in a higher percentage than the general population, or a higher percentage than the 47%. Step 2, check the central limit theorem conditions. Random, look for the word random. Is it in here? It should be in here. Random sample, there we go. All right, large sample. Just go through and multiply this out. You need to get 10, bigger than 10 for each one of these two products. Large population. So you got 54 political scientists. If you go through and you multiply by 10, the population needs to be, more than 10 times the sample. So the population, if the sample is 54, then the population needs to be bigger than 540. Are there more than 540 political scientists who live in Florida? Probably. It's a little hard to check on that one. Most of these the answer is very obvious, but if you went around and asked people, are you a political scientist or not, a reasonable guess is that there's certainly more than 540, considering how many millions of people live in Florida. So it's pretty likely. And then the independence condition, again, there's no way for us to check this, just like the earlier time it came up. We could have a chat with the pollster, but we're just going to assume for the sake of, being able to do these problems. All right, so step 3, first, you're going to calculate the test statistic. So start off by plugging the information from the problem into the standard error formula. So you've got, this P0 is 0.47, so put 0.47 in. Divide by the size of the sample, and then take the square root, and you get that number. Take that number, plug it in the denominator, and then first you put the sample proportion. So it's about 0.7407 if you go through and calculate it. I think it's 40, so you take 40 over 54. And then you subtract the population proportion, which is 0.47. Calculate the result. You get about 4 standard deviations. 4 standard deviations is a large number. It's very far from 0. So our expectation should be that the p-value is going to be very small. All right, so to go through and check on that, we're going to calculate the p-value itself. So open the normal calculator, select greater than. Again, greater. We want to select the inequality in the normal calculator that matches with the inequality from the alternative hypothesis. And then go through and enter your z-value, your test statistic, and hit compute. And when you do that, you get 0.003365. That's a very small p-value. All right, and we can see here that is what the normal calculator looks like in StatCrunch when you enter all that stuff in. And then how do we go through and interpret that? Or sorry, how do we do step 4? Step 4, since the p-value is less than the significance level, that suggests that the null hypothesis is wrong. So we've got to go through. So if you go through and you assume that the political scientists vote at 47%, all right, let's go through this again. So if we assume the political scientists vote at 47% and then 74% actually vote, then that suggests that 47% is wrong. There's a very small probability that 74% would vote when, that you randomly would get a group of 74% who vote when the actual percentage is 47%. I just want to keep reiterating that is how hypothesis tests work, is you go through, you assume the null hypothesis is true, then you do an experiment, and if the probability is small, then that suggests that your assumption that the null hypothesis was true is what's wrong. So we reject the null hypothesis, and that suggests that the political scientists do not vote in the same proportion as the rest of the population, that they do vote at a higher percentage. All right, so that is the first example. Let's go through another example with all 4 steps. So health professionals are often concerned about our lifestyles and how they affect our well-being. A group of medical researchers knew from previous studies that in the past, about 39% of all men between the ages of 45 and 59 were regularly active. Because regular activity is good for our health, researchers were concerned that this percentage has declined over time. For this reason, they selected a random sample of 1,927 men in this age group and interviewed them. Out of this sample, 680 said they were regularly active. Conduct a hypothesis test with a significance level of 5% to test whether the proportion of active men has declined. All right, so first we're going to need to, step one, create the rival hypotheses. So you got to read the problem carefully. All right, so what is the population amount? What's the baseline? The baseline is 39%. That is what it was in the past. And we're comparing, our sample to that. Okay, and then what are we checking for? Are we checking that are we checking for something bigger? Are we checking for something smaller? So the researchers think that this has declined. So that decline word, that is what suggests the less than. So we've got our null hypothesis, which is that the population is still 39%, that it is not declined. And then our alternative hypothesis is that, yep, those researchers are right, and we have seen a decline in the percentage of men who exercise regularly. All right, so that's step one. Step two, we got to check the central limit theorem conditions so that we can use the normal distribution later in the problem. So the random, do we have random? Let's take a look. Random sample of 1,927 men, that is satisfied. And then is the sample large enough? So I'll go through, do the math. You get 752, 1,175. Those are both much bigger than 10. Large population. All right, so we've got 1,927 men in this sample, and clearly there are much more than 19,270 men total between the ages of 45 and 59. There are millions of men that are in that age group. And then independence, again, for the third time, we assume the pollster met this requirement. In the real world, you'd have to talk to them. Step three, we need to go through and do a bunch of math. So calculate the test statistic. To do that, take the population proportion, put it here, divide by the size of the sample, do the math, you get this number, take that number, put it in the denominator. This is the sample proportion, so the 0.3529, where is that coming from? That is coming from 680 said they were active out of 1927. You divide those two numbers and you get the 0.3529. And then minus the population proportion, which is right there, 0.39, and then divide by the standard error we just calculated. When you do that, you get negative 3.339. That is also a number that is far from zero. So again, we've got a result, we got a test statistic, which the fact that it's so far from zero suggests that it's unlikely that this unlikely that the null hypothesis was correct. It's likely that we're going to get a very small probability. But let's go through and calculate it. Let's skipping ahead here. So to calculate the p-value, open the normal calculator in StatCrunch, select less than, that's the alternative hypothesis, and then enter the test statistic we just calculated and press compute. When you do so, you're going to get 0.0004204. And here you can see that gives you all the stuff that's actually in StatCrunch. So it does verify what I just said. And then the fourth step is to go through and figure out what are we going to do about the test itself. So since the p-value is less than the significance level, that suggests that we reject the null hypothesis again. So the same outcome as last time. We went through, we assumed, what did we assume? We assumed that the 39% of all men were active. Then we went through and did a study and to check whether the 680 out of 1,927 men, is that close to 39%? And it turns out, no, it's not. It's far enough away that it suggests that it's unlikely that the modern amount is actually 39%. So it suggests that the alternative hypothesis is the one that's correct this time, and that the percentage of men has declined. The proportion of men who are active has declined, not the proportion of men who in existence. So this is the proportion of men who are regularly active. Okay, and then one more homework example that'll finish up this video. So it was determined that the percentage of A's in the English language in the 1800s was 12%. A random sample of 600 letters from a current newspaper contains 63 A's. Test the hypothesis that the proportion of A's has changed in modern times using the 5% level of significance. That's just 5% written as a proportion. Treat the newspaper as a random sample of all letters used. So it wants to treat this result here as our random sample. All right, step one, create the rival hypotheses. So what do we got? What's the baseline? So the baseline is that the percentage of A's in the 1800s was 12%. So 12%, that's going to be our null hypothesis, is that the proportion is still 12%. And then are we guessing that it's gone up, gone down, so test the hypothesis that the proportion has changed. That's another way of saying that it's different, okay? But it's not specifying greater than or less than. And if it just says it's different, then that's the same thing as saying that it's not equal to. So it was 12% in the past, and we're just checking to see whether it's different in modern times. All right, to go through and use the normal distribution calculator in step 3, we first need to check the central limit theorem conditions. To do that, so random, do we have a random sample? A random sample, yes, it's a random sample, so that is satisfied. Large, is the sample large enough? So go through and do oh, it's only barely large enough. 12 is greater than 10, but only barely. And so anyway, go through and calculate these. You do get bigger than 10 for both of them, so the sample is large enough. Large population. So this is going through and saying, so the sample was 600, so we need at least 6,000 written letters of, oops, English, there's a typo there, in all of the English language in modern times. And of course, there's much, much, much more than that in all of the written English. A single paper has more than 6,000 letters. And then finally, we're going to assume the independence condition again. All right, so calculate the t-statistic by taking the population proportion here and here, sample size there, just plug it in, take that number, that's the denominator, that's the standard error, put the sample proportion here, that 105, where'd that 105 come from? 63 divided by 600, so we got 63 successes, you know, in terms of the versus 600 total. So that's the proportion of A's. So that's the proportion of successes. So 0.105, and then put the population proportion here, subtract them, divide by the standard error, and you get the number of standard errors, or standard deviations. I guess you could think of it either way. So this is the number of standard errors that the z-score is away from 0. That's actually not terribly far, right? So one standard deviation, if you remember, the area or the probability that is close to that is within one standard deviation of the center of a distribution is about 68%. So this number is going to be pretty large with only getting a z-score of negative 1.13. That's going to be pretty close to the 34th percentile, which anyway, you go review the percentiles. But if you got 68% in the middle, then you've got, oh wait, no, it's not 34 percentile. Oh my gosh, I made a mistake. So if you got 68 in the middle, right, then you've got 32 at each end, which means that's the 16th percentile. Anyway, okay, I should just cut all of that out of the video, but I'm going to keep going. So next, calculate the p-value. So open the normal calculator in StatCrunch, select between, enter negative 1.13 in the left inequality and 1.13 in the right inequality, then press compute. The result is going to be p equals 0.7415237. And that's kind of what I was just talking about, is how the probability is going to be really large. So this is the probability between the tails. This is the middle stuff. This is the stuff between negative 1.13 standard deviations and positive 1.13 standard deviations. So again, that's, you know, see how that close that is to 68%. That's from the empirical rule that we covered earlier in the course. All right, so but that's not what we want. We don't want the probability that's between the tails. We want the probability that's in the tails. So we need to go through and subtract that from 1. So you take 1 minus that, and you're going to get about 26%. And if you're totally lost, you're like, I need a picture, and this is the picture. All right, so from 1 standard deviation to the left to 1 standard deviation to the right, that's 68% according to the empirical rule. We have a little more than 1 standard deviation to the left and a little more than 1 standard deviation to the right. So that's why we get a number that's a little bigger than 68%. And of course, that's not what we want. We want the stuff that's in the tail. So that's why we take 1 minus that. All right, finally, get to the last step. So since the p-value is 0.258, and that is greater than the significance level of 0.05, that means that we fail to reject the null hypothesis. There is not enough evidence to support the claim that the proportions of A's has changed since the 1800s. So that kind of, the null hypothesis suggests that the null hypothesis is correct. Okay, so hopefully that's the video. I'm just hopefully that made sense and that you feel like you can go through and you can do hypothesis tests now. And that is the video. Thank you for watching, and I'll see you next time.